Okay, so here's where we were last time. We were talking about limits, multivariable limits, and trying to figure out how to relate this to our existing understanding of single variable limits. Right? And one of the temptations is to say, well, let's try to understand this multivariable limit by looking at paths, right? Let's take some path here. There's a parametrized curve. X is a function of t. That's some parametrized curve through the domain. And let's make it a path that goes through our base point. Where x is approaching this point A. So let's have this path go through A at t equals 0. Why not? Right? And let's try to relate the idea of the multivariable limit to the idea of, well, what's happening along that path? In other words, as t approaches 0, notice as t approaches 0, that means that our parametric curve is approaching A, and that's what we're trying to understand. We're trying to understand the limit as x approaches A. Right? So you might say that when you parameterize a curve through your point A, that you're looking at a kind of one point of view on that multivariable limit. Okay. And so we did see previously that this idea of looking just at straight lines, this was dramatically not good enough, right? Even if you look at all possible straight lines through a point, even if along all those straight lines you get the exact same value of the limit, it doesn't really, that does not address the multivariable limit. And this example that we went through illustrates that pretty dramatically, I think. That here, all straight lines through the origin give you the same answer of 0. And yet, if you look along this spiral, you don't get 0. So there is a disconnect, the jump discontinuity, some kind of a weird thing going on there. This limit really does not exist, and the straight line strategy did not find it, did not detect that. Okay, so this approach to understanding multivariable limits by looking at individual paths, this is not a reliable way to understand multivariable limits. But it is a reliable way to show that limits don't exist. Right? So if there is some path, some perfectly innocent path, and if along that perfectly innocent path, the limit doesn't exist, well, then the multivariable limit, the much more delicate multivariable limit, couldn't possibly exist. Right? And then even more useful, if you look at two different paths approaching the same point, and if along those two different paths you get different answers, if you get any sort of suggestion of a discontinuity in this sense, then the multivariable limit does not exist. Okay, all right. So let's. This is the very last thing we were talking about last time. Let's go ahead and look at an example. Here is an example. Let's look at this function here. We're going to approach the origin. Now, let me confess, you could take a polar point of view on this, right? Remember, we do have this really nice tool already developed that if you're approaching the origin, very quickly, if you're approaching the origin, then you are welcome to convert everything into polar coordinates, and then simply require the polar variable r to approach 0. And I don't want to go down that road right here because I want to use this as an example of how to do something different, right? But in this case, yeah, you could make a polar argument to get the same conclusion that we're about to get to here, but I don't want to tell you what that conclusion is just yet. So anyway, let's not use polar for this, even though we could. Okay, I want to start parameterizing curves, right? We're approaching the origin, so I need curves that go through the origin, and I'm going to start with going along the y-axis. So real quick, here's a picture of our xy plane. Here's our origin that we're approaching, and I want to approach along the y-axis, so we're going to be doing basically that, right? And so I need to figure out how to parameterize, I'm going to parameterize that line. Let's parameterize that line in such a way that the origin is t equals 0, and then we'll take a limit as t approaches 0. Okay, how do I parameterize this line? Oh, well, flashbacks to earlier sections of this book, right? We have to, how do you parameterize stuff? And take your pick of your method, but here's a nice option that parameterizes that line. How we doing? Everybody okay so far? Okay, having parameterized it, keep in mind what a parameterization is. A parameterization is a formula telling you x as a function of t and y as a function of t. So plug all of that in. Everywhere you see x, you put 0. Everywhere you see y, you put t. And plugging in like so, you get, you get this expression right here. Now, be careful with this. You don't want to conflate that which is 0 with that which is approaching 0. They're not the same thing, right? There's a temptation. So a lot of students make this mistake. A lot of students are actually kind of shaky on single variable limits. But it's all too common to say, oh, well, this is 0 over 0 because t is approaching 0. Right? This is not valid. In this parameterization, x is 0. It's not approaching. It's none of that nonsense. It is actually 0. So that numerator is actually 0. That's an honest 0. Now, what's in the denominator? Well, we have, let's see here, 0 squared plus t squared, so that's why we get the t squared here. That is not 0. In fact, now again, there's this temptation to interpret, oh, well, t is approaching 0, you want to interpret it as t is 0, but in fact, it's quite the opposite. Approaching 0 means I want to explicitly ignore the possibility that t might be 0. I'm scared of what happens when t equals 0. I want to deliberately avoid it. So, in fact, when you see t approaches 0, that means t is never actually 0. So, this is not 0 divided by 0. This is 0 divided by not 0. Everybody on board? Okay. Very common sort of misunderstanding there. So algebraically then, ignoring limit, no calculus required, 0 divided by not 0 is 0. And the limit, as I don't care what happens, any limit of 0 itself is 0. That's why we get 0 here. So this is not some sort of indeterminate form, and this is not, undefined. This is flat 0. So make sure you're comfortable with that argument. If you are perhaps a little shaky on your single variable limits, let's talk about it in office hours. Let's get that all polished. Okay, now, so what do we conclude from this? Did we just compute this limit? No, certainly not. We just computed what happens as you approach along a single line. That's it. We haven't even looked at what happens as you come from different directions. So there's no real conclusion here. This is just the first step in a process, and let's take some next steps then. Okay, so now we're going to look along other lines like this. So y equals mx. How am I going to parameterize y equals mx? Well, again, options, different ways that you can go. I'm going to suggest that we use the graph parameterization. Again, big fan, right? I encourage you all to capitalize on that whenever you can. Y equals mx. The graph parameterization then is this. T, mt. Flashback if necessary to the section on parameterizations if you don't remember how to do graph parameterizations. Okay, again, remembering that a parameterization means that is your formula for x, and that is your formula for y, and plug it in, do a little bit of algebra, and you find yourself looking at that. Okay, now what do we do with this? Again, you got to be careful with your single variable limits. You cannot just say, "Oh, t is approaching 0, so look, this is 0 over 0." So undefined, right? That's not what a limit is. Again, t approaches 0 means explicitly that t is not 0. Because t is not 0, I can look at the common factors of t in the numerator and denominator, and I can cancel those as common factors. Right? Thankfully, there's exactly the same number of t's in every one of the terms, both numerator and denominator. That was a lucky break. You won't always get that lucky. But here, all the t's just cancel, and in fact, what I find myself looking at is, in fact, the limit of something that doesn't have any t's in it. We're looking at a limit of this constant, m over 1 plus m squared. And so the limit is m over 1 plus m squared. Okay. Everybody happy? What have we proved? Is this the answer? I mean, is this the value of the limit? Well, no. This is what you get when you look along this curve here of slope m, this line. So what? Well, we're almost there. In fact, it's a matter of sort of making an observation and spiking the football at this point, and that is, notice we never said what m was. Right? We just parameterized this line of slope m, whatever that might be. The answer, no matter what m is, the answer will be this. So in fact, we just actually computed limits along infinitely many different lines. And even though there's a single formula giving us the answer, notice that this formula gives us different values for different lines. So specifically, if we look along, let's look at the line where m equals 1. Then the limit along that line with m equals 1 is, well, let's see here. You plug in m equals 1 into here, and you get 1/2. Right, now let's look along this line where m is equal to 0, and the limit along that line is, okay, well, let's plug in m equals 0 into here, and we get 0. And notice that we have two different answers along two different paths. We have a total disconnect. This is this is suggestive of some sort of a weird discontinuity, and the limit, the multivariable limit, could not possibly exist. We got conflicting answers. Everybody on board? Okay, by the way, quick observation. Notice that means that this first calculation here was kind of a waste of time in some sense. I mean, we went to almost as much trouble to compute along a single line as we did computing along infinitely many lines that allowed us to effortlessly find the contradiction we're looking for, right? So most of the time, I would say start with infinitely many lines and hope that that works out better for you.
Could you stop, like, once you got the first 0,
Yep, sure, quite right. Yeah, absolutely. You totally could have. And the only reason I carried it forward is because I wanted to instead point out that this was a waste of time. But you're absolutely correct. This also was a waste of time in some, given the circumstances. Yeah.
So if you computed the initial limit using the polar coordinates,
yeah,
you would just get cosine theta times sine theta.
Yeah.
You'd still have to make an argument there. So what you'd have to say is, okay, well, let's consider then, you have to do something analogous to this. You'd have to say, well, here are two curves along which I want to approach. There, instead, you would say, let's start approaching along theta equals 0. Then this formula gives us this answer, right? And then let's approach along theta equals, pi over 6. And then you get a different answer, and then you'd say contradiction. So you do have to, you got to carry it through, but yeah, that's how that would work out. Yep, totally fine. Yep.
So if this was a different limit and all the lines actually did work, but would you just like keep going? To
Yeah,
the one that you
that's my next example. Yeah, no, that's a great question. So I'm going to answer your question by going to the next example. And by the way, I'm going to start moving more quickly because the reason I went slowly in the last example is I want to emphasize this process of how to parameterize a line, a curve even, and then how to plug in, etc. So now I'm just going to start moving significantly more quickly here. Here's a question. Notice we are approaching the origin. By the way, that temptation to use polar coordinates, look at your denominator down here. That has x to the 7th plus y squared. In polar coordinates, that's not going to simplify nicely. So I don't suggest using polar coordinates here. This would be super weird in polar coordinates. But anyway. Okay, so let's go along all the straight lines. There they are. You find yourself looking at this limit. Now again, slow down, be careful. You want to start canceling factors of t. And you'd like to cancel a bunch of them. Look at this, you've got 7 factors of t in this term. Right? But you can only cancel common factors of t. And sadly, this term over here only has 2. You can only cancel 2 common factors. Cancellation only gets you to this. Yeah. Okay, so now what do you do with this limit? Another flashback to Calc 1. Right? Single variable limits. A limit of a fraction is a fraction of individual limits. Be very careful, not always, right? Only if both the numerator and denominator individual limits both exist and the denominator limit cannot be 0, right? If those conditions are not met, then if you just say, oh, limit of a over b is limit of a divided by limit of b, if you just write that down, even though the conditions don't apply, and just proceed, you have proceeded into garbage. What you're writing is nonsense. You got to make sure that that's the case. Now, in this case, let's look at these individual, like the limit of the numerator. T approaches 0. Just looking just at the numerator, 0. Cool, no problem there. Limit of the denominator. T approaches 0. That term goes to 0. That term is just m squared. It's not going anywhere. M is a constant for this calculation. So here I get 0 divided by m squared. M squared is not 0. Well, okay, we better indicate somewhere that m is not allowed to be 0. Right? And then I have 0 divided by not 0, and that's okay. So this step here, this I've just kind of used one equal sign and going from here to here. There's a bunch of single variable calculus in here. Make sure that you're good with that because, if you're single variable, if you can't operate single variable limits, then you don't have the tools to deal with the multivariable limits. Okay. So we got all the same answer. We've checked all the straight lines, well, except for that, right? Except for the horizontal. And we're not optimistic about that one. Well, practically all the straight lines, we get the same answer from every direction. We feel this overwhelming urge to say, and therefore the limit is 0, but we resist this urge because straight lines are just not good enough. You've got to consider curves and spirals and knuckleballs and every possible weird curve because who knows, they might be different. So this tells us nothing. Everybody on board? Be careful. So tempting to want to celebrate there. Okay, so now here, there's a parabola. And by the way, if I wanted to turn this parabola into a bunch of parabolas, I could just put a k in front of the t squared. Then I would have lots of parabolas. Suit yourself. Still get 0. By the way, again, make sure that you can do the single variable calculus. And now things start to seem kind of silly because for crying out loud, we just checked all the straight lines and we looked at that you stick a k in there, infinitely many curves.
And come on, we keep getting 0. I mean, what could possibly go wrong here? And then in a very strange deal, you look at a cubic and you don't get 0. So this is a weird function. Doesn't look that weird. Right? This function looks, I mean, for crying out loud, it's just a ratio of polynomials. I'm not doing weird stuff with defining theta and, looking at spirals and strange things like we did in the last example from last time. It's a ratio of polynomials. And yet, we get this this kind of thing again, this sort of at least a jump discontinuity. So definitely some sort of a discontinuity. This limit could not possibly exist. So you see, if you had spiked the football after computing along all the straight lines, wildly wrong. And multivariable calculus is just weird. It's just strange. Okay, enough of that. Okay, let's talk about continuity. I hope you all remember continuity from Calc 1. Again, this is flashing way back. We just say that a function is continuous if the function is defined at the point, the limit exists at the point, and furthermore, those values are equal to each other. Right? So same definition here for a real-valued multivariable function. So notice here our domain is Rn. So these are this is a multivariable limit, and continuity is defined by morally the same formula we require for the limit to exist, for the function to exist, and for the limit to equal to the value of the function. Okay, all right. Now, there's different points of view that you can take on this formula. If you can compute limits, then you can decide if a function is continuous. But now, let me take the same statement, right, and take it kind of a little backwards and point out, if you should happen to know that a function is continuous, that's a big if. If you know a function is continuous, you've got a handy dandy formula for computing limits. You want to compute this limit? Bam, there you go, there's your answer. Just take this point A that you're approaching, plug it in as the x that defines the function. There you go. So that's nice. Why did we mess around with all this other stuff? Right? Why did we just spend a bunch of time looking at examples like this one? And the answer is that this limit here, we cannot cite continuity because at this point that we're approaching, this function is not defined. This function is not continuous. So, in fact, the fact that this is not continuous is arguably why we were interested in the limit in the first place. So continuity is certainly not something you can take for granted. Usually, it's just not there when you're trying to compute a limit. So anyway, that's that. So nevertheless, if you know that a function is continuous, that's a big if. You can take that point, plug it into there, and there's the value of the limit. Now, so what about that big if? How do you know if a function is continuous? Well, think it through. We can compute a limit if we know the function is continuous. How do we check if a function is continuous? Well, we have to compute the limit. And there seems to be a sort of a circularity there. You need continuity to compute the limit. You need to know the limit in order to confirm continuity. Yeah, this is a tail-chasing situation, it might seem. But you have some great big tools here that you can use. These theorems here give you a tremendously large category of functions that have already been shown to be continuous, and you may cite these facts at your leisure. So, all polynomials are continuous. You don't need to prove it. It's been proved. You may simply cite.
Trig functions are continuous where they're defined, and I do be careful about this point. I am not saying that trig functions are continuous everywhere. Certainly not tangent. Tangent's got a bunch of big discontinuities in it, right? Sort of infinite discontinuities. And at those points, the trig functions are also not defined, right? So, this is a big disclaimer, right? So, where they are defined, where tangent is defined, it is continuous. It is not defined everywhere, therefore it is not continuous everywhere. Okay, likewise with these other functions listed, and this is a tremendously huge category of functions. Furthermore, if you add two continuous functions, the result is continuous. If you multiply two continuous functions, the result is continuous, etc., etc. The only little landmine here is when you divide, just make sure that you don't have 0 in your denominator. That's no fair. Okay. All right. So, how do you compute this limit? And this, at a glance, looks like a really hard problem. Look how nasty our objective function is. Until you realize that, well, there's nothing bad happening this function. 2, 1, 3, you plug in, and there's nothing. We're not taking a square root of something that's borderline 0. There's no logs in here. There's no trig functions. In fact, the numerator is continuous. The denominator is continuous. The denominator's limit is not 0. Therefore, this fraction is continuous. We're taking a limit of a continuous function, plug in. That is. So, heads up for continuity. Sometimes this is a useful tool for computing limits. Of course, the far more important purpose of continuity is that it is a regularity condition that allows us to state and prove other theorems. Right? The fundamental theorem of calculus. The version of the fundamental theorem of calculus that y'all have seen in Calc 2 classes requires that the integrand be continuous. So that's why continuity is really important for other theorems. But anyway, in this context, it's a computational tool. Okay, there's some discussion here of vector-valued functions. A short version of this is that if you're taking a limit where you have multiple output variables, everything we've looked at so far was a single output variable with multiple input variables. Here, if you also furthermore have multiple output variables, I just wanted to make the observation that the limit of the vector-valued function is exactly as you would hope and expect, the vector of individual limits. So that just kind of needs to get said, and that allows you to slightly extend the above observations about combining known continuous functions. Anyway, y'all can read the rest of that. Okay. All right, moving along, linear algebra. So we're done with 2 chapters, which is amazing. Feels like we just got here, but we're already into chapter 3. Chapter 3 is a short chapter. I hope to finish it today. It's a really important chapter. It turns out that linear algebra is the best language in which to discuss multivariable derivatives, as it turns out. So let me show, first I'm going to start by showing you kind of what we're up against when it comes to multivariable derivatives. Now, just as a flashback, y'all remember single variable derivatives, f prime of x. Okay, so, limit as h approaches 0, f of x plus h minus f of x over h. All right, hope everybody remembers that definition. Okay. Look, if we're considering now a vector-valued situation, if we're considering a function of vector inputs, so let's look at a function from Rn to R1. We'll just keep the outputs real for the moment. We'll worry about vector-valued outputs later. Turns out that's no big deal, but anyway, let's just keep it real for the moment. No pun intended.
And let's just try to adapt that definition. Let's just do the same thing that worked out so great in Calc 1 classes. Seems like we ought to write down, I guess, so f prime of x. Okay, now wait a second. What goes into the function is a vector, so we better make this x vector. The derivative at a point in our multivariable domain is limit h approaches 0. Now let's just start writing down the usual. So f of x plus h. Okay, whoa, now slow down. Wait a second. This h thing, this h is what we were adding to our x in our domain. This represents that, we're going to move a little bit away from that point to see how the function changes. So, well, if this x is a vector, a displacement from that location should be the addition of a vector. This should be h vector approaching 0. I mean, I'm just thinking out loud here, by the way. Right? Okay, so that minus f of x over h. And can't we just do something like this to define derivative? What's wrong with this? We're looking at how much the function changes. We want to look at the ratio, just like we did in Calc 1, of output change over input change. Rise over the run. And here's what's catastrophically wrong with this attempt. I don't know how to divide by a vector. That's not a thing. Right? So, this whole approach that we took in Calc 1 has just crashed and burned fabulously. Everybody see the problem? Can't divide by a vector. So we are in a weird situation here then. So we're going to have to think up different ways to understand derivatives. And we'll do that possibly as early as today, depending on how fast I move through Chapter 3. But we will do that. We'll make sense out of different ways to think about derivatives. And we will extend to the multivariable context a perfectly reasonable and familiar point of view on derivatives from the single variable context. So that's going to happen. It's just not going to be this one. Okay? And it turns out that in that extension, when you're doing a multivariable analog of derivatives, it turns out that the best tool for that is an object of linear algebra. And you can kind of dance around it in certain ways, but it's much more natural and easy to just say it as it should be said in the language of linear algebra. So we're going to do just a little bit of linear algebra first, and not much. By the way, those of you who are engineers will see a lot of this again in Math 216. This is just a sort of a tip of the iceberg kind of a deal. But anyway, so here we go. So reminder, vectors. Don't forget we're going to use this vertical notation for vectors sometimes. Here's where we're going to really use it quite a bit to write vectors vertically. Arguably doesn't matter, but it ends up being very convenient. I need to define a term called a linear combination. A linear combination of vectors. If you give me a list of vectors, v1 through vk, a linear combination simply means this expression. Linear combination is anything that you can get by taking those vectors that you were given, multiplying by real scalars, and adding. So, instead of linear combination, perhaps a more relatable name for this construction would be, a multiplying and adding combination. We're just combining these vectors by multiplying and adding. Anything that you can get by this sort of, there's lots of different ways that you can
take a list of vectors and choose to multiply some of them by different constants and others by different constants and add them to get some result. So lots and lots of different linear combinations. The structure here is what we're talking about. Okay. Certain point of view, by the way, says that this is the sort of the cornerstone idea of linear algebra. Anyway. Okay. So I want to define a function called a multivariable, called a linear transformation. This is a kind of a multivariable function. So notice we've got several input variables. We've got several output variables. Thus multivariable function. And here's what it means to be a linear transformation. Linear transformation. By the way, another one of the fundamental objects of study of linear algebra, something called a linear transformation. So this is a really big deal. And it's a kind of a disappointing, it's an anticlimactic definition. But here it is. If the function always satisfies these rules, that's it. So the function just has to have the feature that when you add two input values, you effectively just add their output values. And it has to have the feature that when you multiply the input by a scalar, that you're effectively multiplying the output by that same scalar. That's it. And it turns out this is crazy important. And a very, very common kind of function to show up prominently in how you understand calculus of general functions. As it turns out. Now, what these things look like, we're going to develop those ideas, throughout this rest of the section. How do we represent them? Again, we'll talk about that over the rest of today's lecture. But that's what the requirement is. Now, an alternative way to write the same thing is this. I hope this is pretty plausible. I mean, if the function behaves in this highly convenient way when it comes to adding inputs and when it comes to multiplying, scalar multiplying inputs, well, look, all we have here is a linear combination, and this is just kind of, we're adding and we're scalar multiplying. Right? So all this says is if the function plays nice with addition and if it plays nice with scalar multiplication, we could say that differently as the function plays nice with addition and scalar multiplication. It's arguably the same. So I hope that seems believable. Some books make this the definition and then call this a theorem. That's what I'm doing. Some books make this the definition and then call this a theorem. These are what we call equivalent definitions. It doesn't really matter which one you use. They're the same. Ultimately, they're the same statements. Yeah?
What exactly is the T doing? Is it like a replacement for F?
That's right. I mean, you can think of it as F if you like. I'm going to use T. First of all, you don't want to get too attached to any single letter of the alphabet, right? But yeah, it's just T is a function, and I'm using T here, I guess, as kind of a syntactical reminder that this is a linear transformation. And for whatever reason, it is just common in math to use capital letters to represent linear transformations. There's no particularly important reason. Yeah. Mm-hmm.
Is it common in math to spell it with two F's?
Oh, great! Thank you for that question. I always forget to mention. So it means something different. So good catch. This looks like a typo, doesn't it? This means something different. If means that whenever this is true, that is true. Right? IFF is an abbreviation for if and only if. And that means that the implication goes both ways. That's a great question, and I don't know why, it always slips my mind that y'all haven't seen that little notation before. I saw this for the first time 30 years ago. It's just really, I'm so accustomed to it. Yeah. Does that make sense? Is that good? Okay. Here's another pretty plausible rewrite. So this statement about linear combinations of a pair of vectors, again, I hope not too surprising that it's equally true if you're taking a linear combination of more than two vectors. Any sort of linear combination. A linear transformation plays nice with any sort of a linear combination. If you linearly combine before you plug in, that's the same as doing this linearly combining in the same way after you plug in. So the linear transformations just, I like to say, play nice with these kinds of operations. All right, now here's a picture of what this looks like. So here's our first vector v1. It has as its image some vector in the target. Here is some other vector v2. Let's say it has this image in the target. So blue to blue, green to green. You see a couple of points there of what t does. T, by the way, is a function going from the domain on the left to the target on the right. And linearity looks like this. Linearity says, I wanted to go into highlighter mode. Linearity says that if you have a linear combination of green and blue, right? Remember, parallelograms are kind of a visual tool for taking a linear combination. So some multiple of v1, right? Some multiple of v2. Here I have what I'm calling c1 here is like 1.5, right? And then my c2, the thing I'm multiplying by v2, is about half. Yeah. So this parallelogram represents a linear combination of v1 and v2. This parallelogram over here represents a linear combination of t of v1 and t of v2, the same linear combination, note about 1.5 of the first vector, about half or so of the second vector. So when we say linear, when we say t is linear, what I mean is that the function takes the linear combination of inputs and gives you as out the same linear combination of the individual outputs. You might say that the linear transformation takes this parallelogram to that parallelogram. You might say combining before the function, combining after the function makes no difference. Different ways to think about this. Anyway, this is kind of a picture of what linearity looks like. Okay, and we'll draw more pictures. So first and hopefully quickly a brute force calculation. This is just a take a deep breath and plow example, but let's show that this is a linear transformation. This is from R2 to R3, so notice 2 input variables, right? 3 output variables. Want to show that this is linear. The way I'm going to show that it's linear is by putting a linear combination in. I need to confirm that I get the appropriate linear combination out. That's just what linearity says. Heads up, notice I'm using a different notational convention. Instead of C1, V1, C2, V2 here, I'm using X and Y for the vectors. No reason. I just want to kind of mix it up notationally. And instead of C1, C2 for the coefficients, I'm using A and B. Again, that doesn't mean anything. It's just different people make different choices at different times. You got to be kind of accustomed to all of these examples. So what I need to show, linear combination in gives you linear combination out. This is straight up just the definition of linearity. So let's do it.
This is again, take a deep breath and plow kind of a situation. So that first input vector x has got coordinates. The second input vector y has got coordinates. I can combine by coordinates. That's a chapter 1 calculation there. Now notice I've got a first coordinate and a second coordinate to go into the function. X1. So that goes there, and thus lands there and there. And this, there, and thus ends there, and there. Now all I've done there is just kind of plug in, right? This is my first coordinate, this is my second coordinate. I plugged into here, the function becomes that. Right? There's no tricky curves in that plugging in. Now, we look at this monster, and keep in mind my goal is to show that I get A f of x plus B f of y. So strategically, I kind of know that I need all of my A's and my X's kind of over on the left, and I can see I need all my B's and my Y's kind of over here on the right. So just kind of shuffle these terms around and try to be a little bit organized. And here we go. Terms that have A's and X's in them, those terms, if you just move them all over, factor out the common factor of A, they become that. Just shuffling, right? Likewise, the other terms, take those terms, kind of shove them over to the right, notice the common factor of B, factor that out, and you get this. And lo and behold, I get AF of X plus BF of Y. So like I say, look, it's just plug and chug. Everybody's got to do one of these once in their lives. There are different versions of different kinds of functions for which you might have to do an analogous calculation, but that's what they look like. Okay, linear transformations are, again, a super tool. There's a lot of great things we can do with them. Sadly, not all functions are linear transformations. Don't get linear transformation happy and just start claiming everything in sight's a linear transformation. Not everything is. Right? This function here, not a linear transformation. This is easily observed with a little arithmetic. These two things would have to be equal if this were a linear transformation. A little arithmetic shows that they are not. So this is not a linear transformation. Now visually your tip off is that, well, yeah, look, it's quadratic. That doesn't even look linear, right? And that's, okay, yeah, sure. But looks can be deceiving, and this is how you directly confirm. Okay. All right. One last little quick observation before we go to the next subsection, and that is that for every linear transformation, very nicely, T of the origin always has to be the origin. This is a really cool fact. We're always taking from Rn to Rm. If you put the origin in, you will get the origin out. And this is so easy to prove. This is an immediate consequence of one of the defining properties of linear transformation. Just let that scalar, we know this scalar before, scalar after, makes no difference, right? Let that scalar be 0. And notice that I now have T of the origin equals 0. It's the world's easiest calculation. So the point to this is not that it's not the proof. The point to this is the fact. Knowing that the origin goes to the origin is a big deal. Okay. All right. More neat facts. Now, I want to remind you about standard basis vectors. We talked about standard basis vectors a long time ago, back in, it was a week ago. Right? It feels like forever ago. We talked about a lot of pages ago. It was over 100 pages ago, right? It's been, count the hours. Yeah. Anyway, hope everybody remembers. These are our standard basis vectors. These are the unit vectors that point along the axes. Okay. It turns out these are special in various different ways. We've already seen one example of these being special. Let me just remind you a neat fact about standard basis vectors. ABC is a linear combination of the standard basis vectors. In a special way, and namely, the coordinates are the coefficients. Right? This is a unique property of standard basis vectors. You can write every vector as a linear combination of the standard basis vectors, but particularly in such a way that the coordinates of the vector itself are the coefficients in that linear combination. This is a really special fact for reasons that we'll see more of in Math 216. But anyway, here is another really important fact about standard basis vectors. If you have a linear transformation, and if you know the images of the standard basis vectors, all right, now before I give you the punchline, that's not a lot. Right? T is a linear transformation from all of Rn into Rm. Right? So there's infinitely many vectors in Rn. There's only a handful of standard basis vectors. I'm saying that if you tell me what are the images, the outputs that is, of just that handful of standard basis vectors, then it's like a magic trick, but I can tell you anything else you want to know about that linear transformation. I can tell you its value at every other vector. It's very magic trick-like in the way this statement gets made. Okay. So, by the way, I just want to make sure everybody remembers. So, this notation right here and the lingo that we use to describe it, this says we're taking the standard basis vector and we're plugging it into the function. Remember, what comes out of a function we call an image, right? So, I'm going to pronounce this as we go along through the section as images. The image of this standard basis vector. It means, so when I say image of the standard basis vector, I mean T of EI, or T of whichever E. Okay, so let me prove this theorem. So I'm going to suppose that these are all known, right? T of EI is known for all the I's. And I have asserted that I can compute all other values of T. And here we go. I'm going to compute T of X by first observing, well, I know how to write X in terms of the standard basis vectors. This was our trick that I observed back in chapter 1. If you want to write X, you could write it as a linear combination of standard basis vectors using the coordinates as our coefficients. Then I cite linearity. That's linearity. Linear combination in, linear combination out. And we're kind of done here because this vector x that we're trying to compute T of, I know its coordinates. These T of EI's, those are all known. right? I claimed that I can compute the value of t, and there it is. If I know these blue standard basis images, you give me any vector x that I have highlighted in green, and I can compute what t is because here's a formula for it. So here's another way of saying this. Linearity capitalizes very nicely on linear combinations. Standard basis vectors allow you to get anywhere you need to get with linear combinations. So this is the sort of the perfect 1-2 punch. Every vector is a linear combination of these things, and linear transformations play really nice with those linear combinations. So that's what kind of makes this all work. Okay. Again, big nice punchline though. These vectors, the standard basis vectors, if you know their images, then you know everything. Okay. All right, here's a picture of that proof. You'll notice this picture is not that different from this picture that we drew back here. It's a parallelogram in, parallelogram out. It's just a picture of linearity. Here I just wanted to draw a picture of how linearity is allowing us to do what we wanted to do there. Here's your standard basis vector, first standard basis vector and its image. Here's a second standard basis vector and its image. Whatever those are, if you know those images, then, well, any other input vector, use linearity, and you can find its image. So, yeah, like I say, morally the same picture. Okay. So now I want to make an assertion here. I'm not going to prove this, but this is, I think, pretty plausible. And let's see, how did I had a word for this. Linear transformations deform the domain in a uniform way, what we call a linear way. So there's a uniformity to how things that are in your domain get transformed as they come over into your target. And all of the following observations can be shown, but if you have a couple of parallel lines in the domain, and if the images are lines, which they generically are, the output lines will also be parallel. So all these green lines here are all parallel. All of their green images are all parallel. Another way that this manifests is if you were to look at some little corner, some little region of the domain there, and look at what is the image of that little region. Well, several things have happened. You'll notice that this little rectangle that we started with has it's kind of been, if you will, sort of rotated, and it's been maybe squished subsequently, vertically squished, maybe stretched out a little horizontally, something like that. And now let's look at what's happened elsewhere in this picture. Let's go over and look at this little region. You'll notice I've made my little blue region the same size. I'm just trying to make it the same size as that little green region. And look at what it's turned into. And it's been deformed exactly the same way, right? The green got sort of rotated and squished and stretched. This little blue region, identically rotated, squished, and stretched. So the way linear transformations deform the plane is consistent everywhere in the plane. So anyway, I think that's. I don't want to prove that. It's a little bit of algebra, but that's. I think that's a nice interpretation to have in your understanding of linear transformations. Okay. All right. Okay. Some examples. Let's suppose that I know. So I have a linear transformation here. So linear transformation from R2 to R3. And I'm not going to give you the formula for this linear transformation. All I'm going to tell you is that T of E1 is 1, 2, 1. Let me draw that in the picture here. So there's E1. There's T of E1. And then also we know that T of E2, there's E2. T of E2 is this thing over here, negative 1, negative 1, 3. Okay, so that's the only information that I'm going to tell you about this linear transformation. And the question is, what else can we conclude about this linear transformation with this paltry information given? And the answer is everything. I can tell you anything else you want to know about this linear transformation. I just told you the images of the standard basis vectors of the domain. And everything else follows by linear combinations. So, for example, this vector here, that's E1 plus half E2. Well, its image is going to be T of E1 plus half T of E2, etc. In fact, I appeal to your geometric intuition. Everything in the domain, being as it is a linear combination of E1 and E2, all of those images are going to be linear combinations then of T of E1 and T of E2. So what this function does, simply by virtue of knowing the blue and the green, right? What this function does is it takes R2, the x1, x2 plane, takes this whole plane, picks it up, and sets it down into this plane that I get by looking at these green and blue vectors, and stretching everything out in a kind of a uniform way. So we have actually a pretty good picture of what this function does. And of course we could write down formulas if you wanted to compute specific values, specific input vectors, if you want to compute specific output values. Linearity allows you to do that. Okay. So this is intended mostly as a geometric sort of motivation example. Here's a nice one. Let's see, do I have a... Yeah, here we go. Let's look at this function right here. This is a rotation, I claim. It doesn't look like it. But this is a rotation in R2. Hey, wait a minute. I'm sorry. I'm just looking at the clock and realizing it's a little past 11. This is our break time. So let's I'll pick up with this example after the break, but let's go ahead and take our 10-minute break right now. See y'all in a few minutes.